Welcome, everybody. Thanks for hanging out until 3 o'clock on a Thursday. My name is Jeremy. I am a Postgres engineer at GEICO.
And my name is Gabriele Bartolini. I'm VP Chief Architect at EDB, but I don't want to spend too much time here because the real star of this talk is actually Leonardo. Couldn't be here for family reasons, and he's actually the guy that has done all of the work here, and we'll be talking about what he's done. So with this QR code, you can actually see register to a webinar that we will be doing with CloudNativePG for the full presentation. So actually, Jeremy and Leonardo will be doing this.
Yeah, and I was going to point something out that, Leonardo was supposed to be giving this talk today. I'm going to back up so I don't do feedback. Last minute changes, we were not able to bring Leonardo with us, but we did bring his silhouette. If you look very closely at this photo that he took, you can see him in the picture. This is a whiteboard that actually has the design that we're talking about, and he snapped a photo and dropped it on Slack, because that's how you build things when you have people spread all over the world trying to collaborate together on open source software. One more thing, just go click the big red button. That's going to take you to the CNPG GitHub page, and I'm asking you to do that because this is really a fantastic time for you to get involved in Cloud Native Postgres. There's a whole bunch of really interesting places that you could help out and contribute, and places where you could do impactful, significant, important stuff and jump right in. These were just off the top of my head, about 10 areas that I thought of. Today we're just going to be talking about one of these, which is the cluster management and failover topics. So first, I'm going to take a few minutes and I'm going to talk about a little bit of background of why we need this, and at a high level, the algorithm and the design. And then I'm going to hand over to Gabriele, who's going to talk about pop the hood open and look at how the engine was built and how it works. All right, to sort of set the stage for going through this today, there are kind of just two things I want to briefly touch on. The first thing is that Postgres itself, the Postgres engine, provides core replication capabilities. So Postgres can replicate data. What you download from postgresql.org, you can install it on your laptop, install it on another machine. It can replicate. It gives you APIs to do things like convert a replica into a primary. Remember, Postgres is a single writer database. That's an important thing to remember. It gives you APIs to do things like rewinding, like fine-tuning how replication works. But Postgres itself, what you download from postgresql.org, is not going to do any cluster management, orchestration of pods. If we want to run Postgres on Kubernetes, one way or another, this is something that we are going to have to provide. And the second thing, just to sort of lay the groundwork here, is to understand that Postgres replication is incredibly versatile. And this is with good reason. Postgres can do a lot of things. It can run inside your microwave oven. It can run on a nuclear submarine. Postgres can run on operating systems that you have never heard of before. Believe it or not, it even runs on Windows. Postgres can, it does a lot of stuff, and CloudNativePG provides an unusually high level of access to Postgres's replication capabilities. And you'll see that as I go through some of this. Why would you want that? The reason you're interested in access to all of this versatility is because it enables you to fine-tune some of the trade-offs that are involved. And three of the trade-offs that we talk about the most are the ones that I've circled on here around durability, availability, and performance. But before I can talk about how you might make these trade-offs, we really have to start at the beginning and just talk about how do you configure replication and control this replication through Cloud Native Postgres. So in Cloud Native Postgres, there's really four things that are the most important bits that you need to know about. So I'm going to run through these four. There's a few more on the slide that you can look up later on your own. The first thing, and by far the most important thing, is this idea of synchronous replication. Now, what you download from postgresql.org by default is not going to do synchronous replication. And your microwave oven doesn't need synchronous replication, so that's fine. But if you're going to run Postgres in CloudNativePG on Kubernetes, this is something that you should turn on. I'm opinionated about this, by the way. I do think everybody should run synchronous replication. You get the flexibility to make trade-offs as you want to, but I do think this is an important one. What is synchronous replication? Why do I think it's so important? I want to take just a second, because I think this is important. And like what this is connected to is the most fundamental basic thing of a relational database, which is transactions. All right? And this is what makes relational databases what they are. And what this is really about is a promise that we make to developers, to people who are building on our platforms that like, well, actually, it's almost like you can do whatever you want. You can insert data, delete data, run computations, call functions. We actually promise absolutely nothing, like nothing at all, until the moment that you say the magic word. And the magic word is commit, and every programming language has it. That's the moment at which we make a promise. Like really, up until that point, like, you know, there's no promises. Like nobody's gonna see what you're doing. If the system crashes, it's gone. Commit is the magic moment. That's when we make the promise that like other parallel connections can see the effects of what you've done. That's when we make the promise that if there's failures in the system, your data's not gonna disappear. So that's kind of the fundamental thing. And synchronous commit is directly tied into that, because what synchronous commit, and literally the way it's coded in Postgres, is a whole bunch of the logic is just right inside of the code that handles the commit statement. So what Postgres does is when you say commit, if you turned on synchronous replication, Postgres promises that the transaction that you just did is going to be replicated to at least a certain number of replicas. All right, and that is the number that's right here inside of this stanza. There's also a method. What is the method? Well, just really briefly to kind of explain this, the key, this is just going to go back to Postgres again. The Postgres engine itself, there's one key parameter. That key parameter is called synchronous standby names, and I've circled it at the top. Okay, this is sort of the single most important Postgres setting to control synchronous replication. And the syntax, I've highlighted kind of right below it. I pulled out this commit just kind of as a side note. A lot of people don't even realize that Postgres supports two different kinds of replication, both priority and quorum. And this has actually been in there for almost 10 years. It's pretty cool. The configuration of synchronous standby names has three components: a method, a number, and a target set of replicas. Those are your three things: method, number, target set. The method tells you priority or quorum. The number says how many replicas is my transaction on. And then the target set is like, what are the replicas that are in my target set? And that's important because you could have like 10 replicas, but only 5 of them maybe are in your target set for synchronous replication. Again, back to the flexibility, 100,000 ways to configure this thing. All right, the second thing you need to know about is this thing called data durability. I'm going to take a moment on this one too before I speed up a bit. The reason is Postgres is quite literal, okay? So if you told Postgres, I want you to synchronously replicate to one replica, okay? It is going to do it. It will keep its promise. Meaning, if that replica is unhealthy, everything grinds to a halt. Like, you have to have a replica, right? But this might not be the trade-off that you want. Maybe the trade-off that you want is, as long as a replica is healthy, I want to keep those transactions flowing. But like if the replica is unhealthy, even, for example, say that I'm just running maintenance, and like I'm moving replicas around, I have to pull a pod off of a node. Like in that situation, Postgres itself, if it was told to replicate, it will replicate. Now what cloud native Postgres can do, and this is a cool functionality, the terminology in CNPG is called data durability. And by default, it is required, but you can tell it that data durability is preferred. What that means is you have now given the operator permission that if it knows that one of the replicas is unhealthy, it can temporarily change that and reconfigure Postgres with a different number and bring the one down to a 0 so that the database doesn't go down. This means that you will keep your promise most of the time, but there might be small windows of time where you could potentially not keep your promise, right? So that's data durability. That is a CNPG knob, the second thing you need to know. The third thing you need to know about is that there are 3 settings in CNPG that allow you to directly control the contents of the target set. I'll talk a little bit more about that later. And the fourth thing that you need to know is a Postgres setting. And this Postgres setting is called synchronous commit. And what this does is it lets you fine-tune the behavior of the replication. This is the question, like when I promise the application developer that their transaction has been replicated, does that just mean the replica has acknowledged receipt, it's been received? Or does it mean that the transaction is persisted on the disk in the log for the replica? Or does it mean that the transaction, not only is it in the log, but it has been fully applied to the tables and the indexes and everything else in the database on the replica, right? So you can actually fine tune that with this Postgres setting right here. Now, once you have these 4 tools in your tool belt, you are now equipped to go back and to sort of think through all of the different possible trade-offs. Now, I actually really like Oracle's terminology. This is really old terminology from Oracle Data Guard. But they talk about the idea of maximizing performance, which is their default, maximizing availability, or maximizing protection. And like what I've done here in this table is I've kind of mapped out, like within your Kubernetes cluster, your single CNPG database that has like 3 instances in this example, so 2 replicas and a primary. Using those options that we just walked through, we're able to set up our CNPG to maximize protection, to do any of these combinations. But this is only the beginning. There's actually a lot more than this that we can do. Let's just start with a simple example and a fairly common thing, which is what if I want to have a second cluster for something like DR, right? So like this might be in a second Kubernetes cluster, which is in a different location, and I want to replicate between sort of my primary and my secondary. And in this example, these are both CNPG, but your target really could be anything. You can make all the same trade-off decisions using those configuration options that we just went through for this as well. So here's sort of a maximum performance, which is default. This would be asynchronous replication. You can also do maximum availability, and that means it's going to be synchronous writes as long as that remote replica cluster is healthy and available. But if that remote replica cluster disappears and it no longer registers itself over, then we still continue to accept writes. And you'll also notice in this slide, this is the one example that I have where we're using priority-based replication instead of quorum replication. This is kind of the use case where you pull priority-based out of your tool belt and use it. If you didn't catch this, I have on the left-hand side is sort of showing you the YAML that you'd use for your CNPG config. At the bottom of the slide, I'm showing you how that translates into the Postgres database configuration with that all-important parameter, synchronous standby names. You can also do maximum protection with the replica cluster. This is the one where I want to guarantee. So if my standby cluster is unavailable, I actually stop taking writes and shut down my database. But of course, that doesn't sound very good. But that's great, because the story doesn't end here. We can do even more complicated topologies than this. Like we could say have multiple remote clusters. So here's an example, and I'm again walking through the CNPG, how you'd set up CNPG to do this, where you can have, you could have 3 data centers, right? Or like 3 different locations, and you're replicating between all 3 of them. And in this example, we guarantee that my transaction is in at least one of the 2 remote data centers. But I can tolerate one of those remote data centers not being available. I can tolerate one of my local instances not being available, and the database still continues to accept writes. So this just gives you a taste of how flexible CNPG and Postgres are when it comes to replication. But all of this, I kind of had to explain just to set the stage for the big problem that we find ourselves in the middle of, which is if you're going to support so many different configurations, how in the world are you going to like have automated self-healing failover and like try to make sure that that's done correctly and that the code is maintainable? And like I've gone through code from other projects and other places. I've seen stuff like this stuff gets really complicated really fast. Like when you're thinking about cluster configurations, when you're thinking about like trying to guarantee correctness with databases, this stuff gets really complicated. And this is a kind of a really tricky problem. So here's what happened. We were thinking through this a whole bunch earlier this year, and a thought kind of dawned on us that there was this very elegant and simple solution to this whole problem for us that covered every single different configuration that CNPG could do with a very simple approach. And really, it was just sort of stealing an idea that's been around forever, like decades and decades, and just mapping it over to Postgres. And that's just kind of basic quorum concepts. And like this kind of basic idea that like readers and writers being greater than your replication factor or your count of replicas, this is kind of basic stuff. It's just that normally we think of this in the context of kind of the hot path of reads and writes with other databases. It's not something we usually think about in the context of a database like Postgres, but that's partly because things like quorum commits haven't been super commonly used. So all we had to do here was take these concepts and map them down to Postgres. And what we're doing with this is we're just using it as almost like a gating function. So this is really only, it's not like we're having to evaluate this all the time. It's only applied if like we have a primary database or pod failure and we're asking the question, is it safe to do a cluster reconfiguration? Is it safe to promote a replica to become the new primary? Something like that. So that's the point. So this is going to go back to, you'll notice that Postgres parameter I talked about earlier, the all-important synchronous standby names parameter, okay? And here's how we're mapping it down. The target replica set, that's your n value or your replication factor. The number, that's your write factor. And the read factor is the intersection of promotable replicas with the target set. The easiest way to explain this is just to look at some examples. So if we start with the maximum availability configuration of a replica cluster, this is a really great one to look at for starters. So what we have here, and start by looking at the bottom. So look at the Postgres setting synchronous standby names, all right? So we have, our target set has 3 instances. It has our 2 local pods, and it has the remote cluster, one of the pods from the remote cluster. So you can see there our n value is 3, because there are 3 potential targets for replication. Our W value is 2, because we told Postgres guarantee replication goes to 2 targets. Okay. And what happens if the primary database fails? If the primary database fails, we're going to try to look at our set of promotable replicas. Well, only the 2 local replicas are promotable. We can't like promote the remote one. That's out of our control. So our R value is 2. 2 and 2 is 4. 4 is greater than 3. The check passes. Go ahead. We can promote a replica. We'll take a look at our 2 local ones. We'll just take whichever one has the most advanced LSN, promote that guy. And we can do this, and we're guaranteeing, like, and there's another assumption that writes have stopped at this point. The primary is dead. There's no like ongoing writes that we have to worry about. This is just simply a matter of like, are we sure that we're not going to lose any transactions if we just take the most advanced of these 2 replicas, and we can do that. So now let's look at another one, maximum protection mode with the replica cluster. In this example, whoops, I'll go back. In this example, this is the case where maximum protection, if the remote cluster is not available, we want to stop taking writes. We always guarantee the transactions are on the remote cluster, right? Not a super common configuration for people to do, but we still want things to work correctly. So our n value is 2. We have only one of the local replicas is included in the target set at any time. Now CNPG will automatically, if there's an issue with ACDC2, CNPG will just flip it over to ACDC3. So it'll always include one of the local replicas, but our n value is 2. Our W value is also 2. And that's giving us the behavior that we explicitly wanted of if the remote cluster is not available, we want to stop taking writes. What happens if the primary fails? And here's where you see this, right? There's 2 promotable replicas, but when you look at the intersection, only one of them intersects. So our R value comes out as 1. Nonetheless, 1 and 2 is 3, 3 is greater than 2, the check passes, and we can go ahead, we'll end up promoting replica number ACDC2. Now let's look at something more interesting. This is the case where we have 2 remote clusters, right? So in this case, our n value is 4. Both of our local replicas and both of the remote clusters, our W value is 3. What happens if the primary fails here? Our replica set is the 2 local replicas. So our value is 2, 2 and 3 is 5, 5 is greater than 4, the check passes, and we can continue. But what if replica number, one of those replicas was sitting on the same node as the primary, right? And that, the node crashed or the node went away for one reason or another. Now in that case, we lose both a replica and a primary at the same time. Now we only have 1 promotable replica instead of 2. And in this case, our R value is going to come out as 1. And this is where you start to see the algorithm kind of shine. Like, it's a fairly complex topology with these remote clusters we have no control over. And this is interesting because now intuitively, if you think about it, it's kind of unlikely that your transaction is going to be missing from ACDC number 2, okay? Because most of the time, like, those remote clusters probably have higher latency links, right? Like usually, if there's, like whichever replica lags the most, it's probably going to be further away. But it's not something we can guarantee. And the goal of this design was to be able to have, and that's the thing, is like there certainly can be situations or conditions for one reason or another, even if it's uncommon, where for some reason one of the local replicas happens to be the lagging replica. So we can't promote replica 2 and be confident, like make a guarantee that we're not losing any transactions. So this is where the algorithm kicks in. and it helps us to determine that the only safe operation, if you want strong guarantees, is that you put the cluster into a state where a human needs to get in the loop and make a decision, which is a behavior that you're asking for if you're looking for this kind of a thing. Now, finally, let's just look at a couple interesting things, which is network partitions. Now, for network partitions, we have one more variable we need to add into the mix, and that's the location of our operator. Okay. Now, the CNPG operator is based on etcd leases. It's using Kubernetes primitives. It's pretty solid stuff. The operator, it matters because the operator, so if we look at this example here, we have a network partition that's taken the primary on one half of the network. So the primary is not crashed. The primary is still running. And there could be clients, there could be applications still talking to that primary database, still trying to commit transactions, save data. There could be customers on their mobile phones using apps, and those apps might be talking to the primary, right? So we need to handle this correctly. The operator, so when you run through the math, the operator is going to determine that it can make a promotion decision, right? So it can go ahead and promote one of those replicas to be a primary. Now, there's an interesting question here, which is why is this not a split brain? The reason is, this is so important to understand, and this is why, I go back, the synchronous replication is so important, because CNPG will allow you to run without synchronous replication, right? And to be clear, there is a fail-safe mechanism in CNPG where that primary, even without synchronous replication, that primary database will realize that it has been isolated out, and it will shut itself down. But there is no possible way to build a system where that primary can shut down fast enough to guarantee that not a single transaction will be committed, right? So again, coming back to keeping our promise, keeping the promise that we make to application developers as a relational database, that we're not going to lose any transactions. The thing that actually protects you here is asynchronous replication. The moment the network partition happens, the primary no longer has a replica, and this is where we want the behavior that I talked about earlier, where, and don't get me wrong, the CNPG's data durability setting is not going to kick in here. So this is not related to that, because the operator isn't going to go in and change the primary settings. It can't. It's partitioned off, right? This is where that behavior of Postgres rigidly keeping its promises is the thing that protects us from data loss. We want that. With synchronous replication, the moment the partition happens, the primary, somebody tries to do a commit, it's going to hang, because they're waiting. It has to be replicated to at least one replica, right? So that's the thing. It's just interesting to think about. That synchronous replication is actually the thing that makes this not a split brain. That's why the primary immediately stops taking any commits or any transactions. Just for the sake of completeness, we'll take a look at the case where you split off one of the replicas. This is pretty boring. The primary has a replica. There is no interruption, and primary keeps on running. The application stays up. The operator doesn't do a failover or anything. You could conceivably replace the unreachable replica. Not a big story. But here's the really interesting case. The really interesting case is this one. What if your network partition puts the operator on the same side of the network as one replica, while your primary is on the side of the network with another replica? Now, I want to point something out. This cannot happen if you only have 3 topology domains, right? If you only have 3 topology domains, your operator is going to follow etcd. Your operator is going to follow the Kubernetes control plane. And as long as you have 3 topology domains, similarly, the operator is always going to wind up on the majority side of a partition, right? And so the same as Postgres. But if you have 5 topology domains, for example, you can absolutely get this thing where the operator winds up on one side of a partition, and with 3 replicas, 2 of them wind up on the other side of a partition. This is the case that's really tricky, because in this case, the operator is going to run the math, and the operator is only going to see one promotable replica, right? So the operator, what's going to happen is the check is going to come in and tell the operator, no, you can't do a promotion. You see one replica, you can't promote it. You can't guarantee. The thing that's also happening is that on the other side of the network, the primary database is continuing to take writes, right? So if we were to do a promotion, we would have created a situation where we fork the timelines and you end up with 2 systems that are taking writes. And this is low-level wall replication that doesn't get, there's no reconciliation here, right? It's not like systems where you can reconcile the changes later. So this is a very just important thing, again, where the algorithm shines, that the correct outcome in this situation is, once again, you want to put the system into a state where a human has to get into the loop and make a decision about how to proceed. All right.
So now let's go to see how this works in CloudNativePG. So starting with CloudNativePG 128, the synchronous replica configuration hosts a new field. It's called failover quorum. So when you set this field to true, the operator enables the failover quorum check for that Postgres cluster and creates a new custom resource of type failover quorum for the same cluster. This resource is named after the cluster itself, and once updated, it contains the information needed to check if an automated failover is possible or not. So the operator is not directly updating the failover quorum, because the ultimate authority of that is the Postgres itself. So Postgres, through the instance manager, basically we update the Postgres configuration. And the status section of the resource contains the structured version of the synchronous standby name setting in Postgres. This will be updated every time the Postgres configuration changes. So CloudNativePG manages the Postgres configuration declaratively, which means that you need to change the cluster resource. When that happens, the instance manager rewrites the configuration files for Postgres and sends a SIG-up signal to the postmaster. In order to make decisions over the automated failover process, we need to be sure of the latest applied configuration for Postgres. So looking at the cluster resource is not enough, because the instance manager may not have received the change yet. And similarly, we cannot trust Postgres configuration, the Postgres configuration file, because the postmaster may not have applied the change yet. So to complicate things even more, given that Unix signals are asynchronous, sending the signal is not enough for us to be sure that Postgres has actually received the new configuration and applied it. So to be on the safe side, we change the failover quorum resource to disable automated failover immediately before sending the SIG-up signal, and enable it again after the postmaster receives the new configuration. So this raises a question. So how can we be sure that the new configuration is actually being received and applied by Postgres? So to answer that, we need to explain how CloudNativePG prepares Postgres configurations. So, I had missed this. Okay, so CloudNativePG adds two settings to the Postgres configuration. One is CMPG synchronous standby names metadata, and the other one is CMPG config SHA-256. So the first one is a JSON version of the synchronous standby name setting, and the instance manager uses that field to update the failover quorum setting without having to parse the corresponding option in Postgres on the fly. The latter is a hash of the configuration content. So to understand if the postmaster received the new configuration, we read the current configuration hash from Postgres and compare it to the one that we expect it to be. And if they differ, the old configuration is still in place. And if they don't differ, the postmaster reads the new configuration. So if the postmaster reads the new configuration, we can proceed with updating the failover quorum object. We then update the failover quorum object with the new content from reading the synchronous standby names metadata. And from this moment on, the operator is able to perform an automated failover if needed and if conditions are met. So if the failover quorum manager is enabled, automated failovers will be authorized only if the requirements are met. When the requirements are met, we have strong consistency, so there's at least a replica that has received all of the rights. And if the replica exists, promoting the most advanced standby is safe, as Jeremy showed before, and we can proceed with an automated failover. So that's all. Again, if you I encourage you to sign to this webinar where Jeremy and Leonardo will give a full and longer version of this talk. So if you have, there's probably time for one or two questions. So, any questions? No. I want to thank Jeremy because I think the work that him and Leonardo have done, I think I've been in the Postgres space for many years. You know my vision about Postgres for Kubernetes if you have been following me, but I think this is an historical moment for this project and for running Postgres in Kubernetes. So thanks for being here and for listening to this talk.